Reaction yields and limiting reactants. First definition, limiting reactant. If I have a reaction, quite simply, the limiting one is what kind of controls it. It's the one that you run out of first. And then in that sense, it limits how much you're going to get for a product. All right, so the limiting reactant is simply which one do you run out of first. And if I have any reaction, like the ones up here, I might have a pile of magnesium chloride, a pile of sodium hydroxide. Unless I plan it very carefully and get them exactly in the right amounts, I'm probably going to run out of one of those piles first when I'm doing the reactant. Right? It's very important to be able to identify which one, because any calculation that I do to try to predict how much of a product I'm going to get has to be based on how much of the one I run out of first. So it has to be based on the limiting reactant. The book has its technique for how to figure out the limiting reactant, and quite simply it works, but I think it's the long way. Let me just describe what happens. They say, hey, take how much they give you of one and figure out, like say how much I'm trying to figure out how much sodium chloride I'm going to get. Do that whole big stoichiometry calculation. Then take how much they tell you give the other one, do the same thing, figure out what you're going to get. And look for the smaller of those numbers. Right? Whichever one produces less, that correctly identifies the limiting reactant as being, in this case, either magnesium chloride or sodium hydroxide. It's perfectly correct to do it that way. I have a slightly different approach that I think works a little better. And let me show you that with example 412. Let's read what they're asking me first. Example 412. There it is. It says silicon nitride, very hard, high temperature, ceramic, blah, blah, blah. Here's the reaction for how you prepare it. 3 silicon solid, 2 nitrogen gases to give you this silicon nitride. Notice they've balanced it for me. It says, what's the limiting reactant when 2 grams of the silicon and 1.5 grams of the nitrogen react? So they're giving me how much of each one of those, and I have to figure out which one am I going to run out of first. All right, so let's copy this down. Here's my balanced equation again. All right. Now notice 3 of these react with 2 of these. That doesn't mean you're necessarily going to run out of this one first. Again, this is just the conservation of mass, my balanced equation. I might have a huge pile of one and just a little pile of the other, right? You can't just predict based on the coefficients. So let's look at how much they tell me I'm actually getting from each one. 2 grams is my pile of silicon. 1.5 grams is my pile of nitrogen. So again, you might look at that and say, oh, I've got less of this. But again, a gram of one thing doesn't have the same number of moles as a gram of the other thing. You can't look at the weights. That doesn't work either. So finally, you might say, well, I've still got less of this one, even if I convert it to moles, and so I'm not comparing grams. But still, hey, 3 of these is required. 2 of those is required, so you actually require 1 more of these. So there's a lot to think about here, a lot to work out. Very easy to figure out which one you'll run out of first. And here it is. And I wrote them out here in the steps up above here. 1, always follow these steps and you'll always get it correct, okay? 1, convert everything, all of those reactants to moles first. We know how to do that. Grams per mole, right? Convert them to moles. Number 2, divide by the coefficients of the balanced equation. So in this case down here, my coefficient for silicon is a 3. It's a 2 for the nitrogen. That's what I'm going to be dividing by. And then number 3, now compare them. Whichever number is smallest, that's the one you're going to run out of first. Simple. Let's see it in action. Here I've got 2 grams of the silicon, 1.5 grams of the nitrogen. So first, convert those to moles. Use the formula mass to do that. For silicon, 28.09. For nitrogen, it turns out to be 28.02. So I convert them. All right, I've actually, that pile of silicon is 0.0712 moles, and my pile of nitrogen is 0.0535 moles. All right, so I actually have more moles of silicon. But again, that doesn't mean I'm necessarily going to run out of it first. Oh, I'm sorry. This is the smaller pile, right? That does not mean I'm necessarily going to run out of it first, though, because, hey, I require more of the other one. I require 3 silicons for every 2 there. So I can't compare them yet. So again, retracing, I've converted them both to moles. The second step, divide by their coefficients. So I've got my balanced equation. This one I'm going to divide by 3. I get 0.0237. This one I'm going to divide by 2. So I get That divided by 2.0268. Now I compare. 0.023, 0.026. Here's my smaller number. I'm going to run out of silicon first. That pile. Even though it weighed more, even though I've got more moles compared to the nitrogens, I'm still going to run out of it first because actually in my balanced equation, I require more. I require 3 for every 2 of the nitrogen. All right, so my limiting reactant there is the silicon. All right, once I've identified that, I could go ahead and do calculations in the normal stoichiometry way. So identify your limiting reactant. With those steps, it will always work. And I don't care if you have 3, 4, 5 reactants, just do the same thing to all of them. Convert to moles, divide by the coefficient, and then compare all 5 of those numbers if it is, and find the smallest one. That'll always give you your limiting reactant. Which one are you going to run out of first? All right, now that we understand that, we can talk about yields. You see, when you actually go and do these reactions in the lab, things can turn out a little different. I mean, it's one thing to do it on paper. Theoretically, hey, I'm supposed to get this much. I've done my stoichiometry calculation. When you go into lab, things don't always work 100%, do they? Even if you've done nothing wrong and your technique was perfect, still sometimes you get little side reactions. Sometimes they just don't react all the way and you get a little bit left over still. So, I mean, it's just never perfect in the lab. And so we've got something called yields. There are 3 types of yields. Number 1, the theoretical yield. This is what we've been talking about all along. This is where you do your calculation and you predict how much you're going to get. Hey, I'm starting with this much, 3 grams of this, and I predict I'm going to get 2.5 grams of this product, right? You do the stoichiometry calculation, just like what we've been doing. That's your theoretical yield. In theory, what am I going to get? All right. Actual yield is number 2. The actual yield, just like it says, what you actually do get. So now you walk over, you get into the lab, you do the reaction, you take the product, you put it on the balance, and you weigh it. Hey, I was supposed to get 2.3. I actually got, according to the balance, 2.1. So I didn't quite get everything that I was supposed to get. All right? That's my actual yield, the 2.1 grams. Okay? So theoretical yield, that'll tell me in grams what I predict. Actual yield in grams, what do I really get when I do the reaction? And finally, the third type of yield we can talk about, the percent yield. This is where I'm going to compare those two. Right? I compare them as a percentage. The actual divided by the theoretical, and then multiply by 100 to convert it to a percent. All right, so, hey, I went in, I should have gotten this, but I only got this much. Turned out to be 85% of what I could have gotten. Right? My percent yield is 85%. That's, I got 85% of what I theoretically could have gotten. That doesn't mean I did it wrong. Again, side reactions, poor environmental conditions for that reaction, reactions that are simply incomplete, they don't go 100%. There's all kinds of reasons why we don't get 100%. And very typically, we get quite a bit less even. That's okay. That's just the chemistry, and we need to be able to describe it and do those calculations. So, example 4.13 from your textbook. It says, calculate the percent yield upon reaction of 1.274 grams of copper sulfate. So you better know how to write that, right? Copper sulfate. There it is. Copper 2 sulfate, more specifically. React with an excess amount of zinc metal. So we've got 1.274 grams of this, and we threw in a whole bucket full of zinc. I mean, we are not going to run out of the zinc, in other words. An excess amount. We know this is not my limiting reactant. We know that the copper sulfate is. That's nice when they tell us that. So now we can do our calculation based on just that. It says we got 0.392 grams of copper metal. Here's the copper. What's the percent yield? So when we did this, that's how much we actually got after we weighed it. Did we get what we should have? Did we only get 90% of what we should have? Right? That's what it's asking. Compute the percent yield. All right, so let's turn over here and see how you actually do that. Here's my balanced equation. Again, I like to write underneath each one what I have or know or what I'm trying to calculate, right? So they told me I'm starting with 1.274 grams of copper sulfate, and they told me when I did the reaction in the lab, I got 0.392 grams of the copper metal. What's the percent yield? So I'm going to have to calculate this. Percent is actual divided by theoretical. I already have my actual, 0.392, so I need to calculate my theoretical. Once I get that, I can divide, and I'll have my answer. All right, so theoretical yield. This is stoichiometry. I've got 1.274 grams of the copper sulfate. Convert to moles. Go from one thing to another using the balanced reaction, which turns out to be just bunches of ones in this case. Go back to grams. 0.5072 grams of copper. Alright, so I've done my stoichiometry calculation. I've predicted I should be able to get 0.5072 grams of copper metal. Of course, I only got 0.392 actually. This is my theoretical. This is my actual. All right. So, to get my percent, I divide them. Actual divided by theoretical times 100, 77.3%. So that's pretty good actually. I got 77.3% of what I theoretically could have gotten. Those are the yields. Know those three and they're pretty straightforward.